Okay, so right now, after talking about the design part, let's get back to the data part in detail. We're going to deep dive into it. Now, first thing you want to address is the qualitative data. Okay. Now, qualitative data is best when it aligns with the quantitative data. For example, if you are addressing or monitoring the rate of reaction by monitoring the color change of a copper 2 solution, okay, and you realize that the concentration goes down, okay, using the spectrometer, okay, and qualitative data aligns when you actually mention that the blue color becomes paler as times go by. And in this case, that you know is aligned, is actually pretty good to write down. Okay, or if it serves the evaluation part. So let's say you find out that there is a percentage error that is underestimated, okay, and your qualitative data you do mention something. Let's say, okay, some bubbles were trapped in the solution or in the delivery tube. Okay, to be honest, even this is kind of low tier evaluation, but uh, if you can't write anything else, then of course you can still write it down. But I think the main point is that for qualitative data, it should serve for something. You're not simply writing down simply because it's a requirement. Okay? Uh, it serves best when it aligns with the data or it aligns with something about evaluation parts. Okay? That would be best. Okay? And moving on is the quantitative raw data. Okay? It's the instrument reading together with absolute uncertainty. Okay? So instrument reading, for example, like usually people got it wrong, is that they only talk about the volume of NaOH added. Okay? But in the titration data, they did not add the final and initial burette reading. In this case, it's not good. Okay? Or if you want to talk about the temperature change, you should have the initial and final thermometer reading. Okay? Or maybe you collect the temperature every 3 seconds. Okay, like you should have these kind of instrument reading data to it. Just make sure the unit is correct, and also absolute uncertainty is correct. Okay, and usually for raw data, okay, you should have consistency in decimal place. Okay, it should align with the absolute uncertainty of the instrument. Now, only if large amount of data have been collected, students are permitted to present only a representative sample of raw data to facilitate comprehension. So let's say, for example, maybe for some of you, you take a whole spectrum, okay, but you maybe only need the maximum absorption, okay. Then, of course, you're not going to provide me every single time the whole spectrum, okay. You just show maybe one of the sample, let me know that you're actually using the maximum absorbance, okay, and then the rest is simply raw data, stuff like that. Okay, it's okay, it's fine. Okay, now how do you process data? Okay, if there are some outliers, you can uh, say that it's an outlier. Okay, and then you should use, okay, one of the trials, okay, to do a sample calculation, so that for the marker, uh, he or she will understand, okay, how you go from the raw data to the process data table. Okay. Now, for example, maybe one of the rate of reaction investigation is how do you uh, find the rate constant, right, from measuring the time used to collect 10 cm cube of hydrogen gas. Okay. Now, in this case, the raw data is the time required to get 10 cm cube of gas. Okay, and then you should have one of the trials to talk about how you use those data and to come up with the uh, rate constant, or maybe natural log of rate constant, because later on you in the Arrhenius equation it requires natural log k. Okay, then throughout this process you need to list it down with a sample calculation. Okay, when it comes to process data, this time, usually, okay, most of the time, now you have to be aware of the significant figures. Okay, uh, because usually it consists of multiplication and division. In this case, then you use the least sig fig. Okay. Bear in mind the unit and symbols are important as well. Symbol means that sometimes you can actually use some symbol uh, to represent, okay, that variable. For example, you use a large T for temperature, or maybe a small t for time. Okay, these are actually good ways. Okay, so that you, or maybe for a marker, it understands, okay, how some of these variables are calculated or collected. Okay. Now, except from sample calculation of the final answer, okay, remember error propagation requires sample calculation as well. For example, you convert from the time required to collect gas to the natural log of rate constant. Okay. You also want to provide, okay, how are you going to make good use of the absolute uncertainty of time, maybe, or with some other kinds of error that accumulated throughout this process, so that you can propagate the natural log of rate constant. In this case, you need to show a sample calculation as well. Now, after all, okay, you should have a process data table where it shows the x-axis and the y-axis of the graph. For example, if you want to have a graph with natural log k against 1 over t, okay, 1 over temperature. Now in this case, in the data table, there should be 1 with natural log k, okay, maybe with its uncertainty as well, together with 1 over t, okay, and its absolute uncertainty as well. Okay, be aware which one is IV, which one is DV. Okay? If it's the IV, it should be on the left column. If it's the DV, it should be on the right column. Okay? And I want to address this, okay, especially for people who study biology. I know that biology requires standard deviation sometimes. Okay, now in this case for chemistry, it's very, very, very rare to use standard deviation. Okay. Let me give you some more details why usually we don't use standard deviation. Actually, when we use standard deviation, there is a underlying assumption behind. Okay, is that we assume that the data that we collect is normally distributed. It's like we can assume we have enough trials so that it can be assumed, right, to be normally distributed. But usually when we say we have enough trials, right, is n greater than 50. Right? 50 is usually the standard for most of the research paper. Okay? And so in this case, think about your procedure. Right? Usually you don't do all the way up to 50 trials. And so in this case, let's say you only do 3 trials. Okay? Then of course using a standard deviation to calculate the error is a huge mistake. The reason is because the assumption can be easily broken simply because you have so less sample size. Okay? Now after talking about the process data and standard deviation, whether we should use it, now we talk about the graph. Okay, the graph should have title, IV x-axis, DV is the y-axis. Okay, the unit and the scale. Okay, you have to be aware of that. Okay, even though most of the time the scale, Excel has already make it nice for you. Okay, make sure you tick the 2 boxes when you fit in the trend line. One of the boxes R squared, another is equation. Okay. If possible, okay, I would say this one, it may not be, even in the IB, it does mention that it's not necessary that you need to add it for error bar and max min line. But I would say if you want to aim for a better work, a high tier work, and somehow if it's, let's say if it's linear graph, okay, it's always better if you add error bar and max min line. Okay. The reason is because when you have error bar and max min line, you have a lot more to discuss, okay, like in the data analysis part. So usually I would say if you want to aim higher, okay, then usually you should add error bar and max midline. Okay. Yes, this is a case where students do ask me, okay, is that should a best fit line a curve or a straight line? I would say it's case by case scenario. Okay? But the rule of thumb is that you are not making a best fit line simply because it has the highest R square. Okay? Now a lot of people would say that, oh, let's say compared to clicking the power or the linear, okay, or the power one seems like have a higher R square. Now in this case, it should be a curve instead of a straight line. Now in this case, I would say it's not good. Okay, the reason is because R square should not be your justification on why you are putting up a curve or straight line. The justification should be based on your literature support. Okay, now for example, let's say Arrhenius equation again. Okay. For Arrhenius equation, it apparently shows that natural log k and 1 over t, they should have a linear relationship. Then in this case, okay, maybe in your data, it's so bad that a curve might have a higher R squared than a straight line, but still you should put in a straight line. The reason is because it's literature support, the theoretical framework is telling you that it should be a straight line, and so you should put in a linear trend line, even though the R squared may be a little bit lower than the curve. So not every single time in chemistry there is a mathematical equation that supports or directly supports that it's a straight line or a curve. Okay, just in case you don't have a mathematical equation to support that, then in this case you should use deduction, okay, through several literature support to allow you to deduce out whether that is a straight line or a curve. Okay. No matter what, the rule of thumb is that you always should have a literature support, a theoretical framework support, okay, to justify whether it's a straight line or a curve. Now, a lot of times I would say, usually, okay, just usually, okay, it would be better if you try to linearize your graph. Okay, the reason behind is because let's say you have a curve graph. Okay, and of course we say, oh, it's good to have error bar and so. Okay, but let's say for a curve graph but with error bar, okay, the limitation is that you cannot plot a maximum curve line and a minimum curve line. Okay. That means even though there is an error bar on a curve line, the usefulness is not as great as the linearized one. Okay. Because we learned from IB is that when there's a linear graph, okay, that means you can easily calculate the slope, you can easily find the y-intercept as well. Sometimes they actually do have scientific meaning. Okay? And so when you're calculating the percentage uncertainty of the slope based on the max min line, or maybe you are calculating uncertainty of the y-intercept based on the max min line again, in this case it provides more, okay, scientific meaning behind. Okay? So let me give you a example. Okay? So let's say is you're talking about how the rate and concentration of HCl, like how do they relate? Okay, and from the theoretical framework, you know it's actually a second order. Okay? That means the rate of the reaction is proportional to HCl concentration square. Okay? Now in this case, of course, you can write down x-axis as HCl concentration. Okay, and you're expecting a curved line with error bar. Of course, this one is actually possible. Okay, but it would be best if you are trying to make x-axis as concentration of HCl and then square. Okay, the reason is because right now once you squared it, now you know that the slope is actually the rate constant, and then you can also check whether the straight line passed through the origin as well. Okay, using the max min line. Okay, so you can actually evaluate whether the uncertainty of the y-intercept does cover the origin. If it does, then it's the uncertainty problem. Okay, but let's say your data is so bad, okay, that the y-intercept is uncertainty actually doesn't cover the origin. Now, in this case, you know that there is a systematic problem, a systematic error in your experiment as well. Okay, so you can actually see in this case, when you're trying to linearize your graph, it shows more scientific meaning behind. Okay, and these are worth discussing and analyzing in the conclusion part, in your data analysis part. Yeah, so as you can see, this is what I actually covered just then. Okay. Well, of course, I would want to mention is that not because a straight line is always better, so therefore, no matter what, you try your best to make a straight line, even though there is no literature support. No, okay. I think the very first rule is that you should have literature support. You should have a theoretical framework, okay, on justifying whether that is straight line or a curved line first, okay. Yeah, so in Chinese we say 谋名强, okay. If you cannot make a straight line, okay, then don't try to make a straight line simply because a straight line is better. Okay. Sometimes, okay, if it's a curved line is better, it fits your theoretical framework, then just use a curved line. Okay. Or let's say one of the examples is, let's say you are providing me a titration curve. Then of course a lot of us would know that it should not be a straight line anyway. Okay. So in this case, if theoretical framework provides is that it's a curved line, maybe somewhere in the middle there's a huge rise, okay, something like that. Then in this case, of course, you follow that theoretical framework. Okay? So again, the most important thing is that no matter what, you have to compare with the theoretical framework. The theoretical framework provides you a picture of whether that is a straight line, whether that's a curved line, whether there's a whatever shape, okay, that you find it reasonable. Right? To me, that's the most important.